interview with one of our fellows. Hopefully this is working, and I am sure that people will allow us to know whether or not something is going wrong via Twitter or YouTube if things are not being said. I'm just going to, Sam, check the Conjecture Institute Twitter stream to see that we're actually live, and we are, so good. I know at least one thing is working. Sam Kuypers is a quantum physicist and a physicist who happens to have worked with David Deutsch, and I'm sure we'll get around to talking about that at some point. What I'd like to begin with, Sam, is for people who don't know you, and people ask me this whenever I end up in situations such as yours, sitting there answering questions. How did you come to physics? What was your journey in falling into this particular subject area? Out of all the interests that you might have had upon leaving school or going through school, you find yourself now an actual professional physicist. What's the story there?
Good question. I think a lot of it started with my dad having himself an interest in physics and endowing that onto me. So he would get me interested in physics problems and we would discuss that. And I think from there my interest grew. It was first that, then discovering Richard Feynman, reading the Feynman lectures and thinking maybe this could be like a university degree. And it's also like I think the kinds of explanations that you had in physics always stood apart from those that I saw in other subjects because they were extremely precise as well as predictive, and they were unusual in those regards. And then at university, I enjoyed it so much that I thought, well, this could be a career, and I've been trying to make it a career ever since. It's my career now.
And you started off, obviously, you are from the Netherlands, and so you went to a university. Which university did you go to in the Netherlands?
I went to the University of Amsterdam and did my bachelor's and master's degree there, and then went to Oxford for a DPhil, and then I've been a postdoc since then.
Oxford holds a very special place on planet Earth, we might well say, in terms of its history with respect to many disciplines, but in particular physics. It holds a special place in the minds, I would say, of the community of physicists. What is it that separates Oxford from any other institution? What makes it special, perhaps in terms of physics, perhaps more broadly? Why were you attracted to that place, and what do you think, what's its position culturally when it comes to physics?
Right. Well, I think there's several answers to that one. Firstly, I got really interested in David Deutsch's books when I was in university in Amsterdam, and then I thought, well, I don't really see the kind of stuff I became interested in, like Everettian quantum theory, was not being done at the University of Amsterdam. And I thought, I would like to be in a place where that is like seriously considered and is given attention, and it's the kind of research I would like to do. And that, to a large extent, was going on in Oxford, still is. I think at some point they called it the Oxford disease or something. I forget the exact term.
Oh, okay.
So it's like, it might have been that, or it might have been quantum computation or Everett. Like, there's lots of Everettians in Oxford. The philosophy of physics department in Oxford has many of them, and like Simon Saunders, who worked on decoherence and branching and things like that, and did really important work. David Wallace is another prime example. And anyway, so that's the kind of thing that I was interested in and I wanted to do, and Oxford was a clear candidate for that. And I guess more broadly, there are just many interesting people that come from Oxford or go through there. Christopher Hitchens, Richard Dawkins, Salman Rushdie, people like that. And I think partly it's so I did not do an undergraduate degree there, but I think undergraduate degrees are very different in Oxford, they're very different from other places. Like there's the tutor system where you have individual sessions with someone who's trying to guide you on a subject. That was not
Right.
really a thing in Amsterdam so much. So my experience of my undergraduate degree was just you go to a lecture, you maybe have some classes where you go through problem sessions with a teaching assistant, and that's it. There's no, that's the extent to which you're being educated at the university, and everything else you either do independently, like maybe there's homework, and otherwise you have your own research interests or your own interests within an academic field, and that you kind of pursue if you want to. It's not necessarily encouraged. It's kind of neutral. The institution is neutral about this. Whereas in Oxford, that's another thing, is that you have lots of student societies where people who are extremely enthusiastic about a topic can pursue that topic with other like-minded people and invite speakers from all over the world. And they have this, I ran a student society for a while, and it's quite nice because you can say, well, would you like to give a talk at Oxford? And people generally say yes to that kind of invitation. And I think, yeah, that might be a thing that exists more in the Anglosphere. I'm not sure how that would be at an American university, for example. I think American universities also have things like student societies, much more so than the Netherlands had. In the Netherlands, it was not really a thing that existed. It's kind of unheard of. You had other stuff. You had sports clubs and stuff like that.
Yes. I think that's precisely the same in Australia. That was my experience in Australia. Sounds more like what it was in the Netherlands as well. This tutor system that operates in Oxford, I wonder if that's an English or more broadly a British thing. I think it happens in Cambridge as well, or if it's just an Oxbridge thing perhaps, or
yes.
Yeah, I
think
wonder.
It also happens in Cambridge. I believe it happens there too. And the benefit I see in that is that you have lots of interactions with someone who is an expert in a field, whereas otherwise, I think it otherwise kind of gets postponed to something like a master's or a PhD degree, where that's kind of when you start really interacting with university staff more. So here, again, I did not enjoy the tutor system. Because I didn't do my undergraduate in England, but it appealed to me. It has a certain appeal. It seems nice to have these informal things which contribute, like the student societies, to learning. I think it's also just like the people there are very driven. That's another thing. Like a lot of it, I noticed that a lot of the fun of being there came from being around other people who were extremely interested in all the things that they were interested in, which sometimes that was physics, sometimes that was politics, sometimes that was philosophy, and you just had a wide range of people to engage with, and that was nice. So it's a bunch of things coming together in a way it's hard to plan that. I think there's lots of traditions that existed there. It's a place that was another thing that really struck me. It's a place with very rich traditions that got handed over to new students in a very short period, and everyone went along with it. So that was also interesting, that you have, when you have to do exam, again, I did not have to do this. I was somewhat happy about this, but when you do exams, you have certain formal dress and you have to wear flowers.
Yes. I remember I was over there a year or two ago, and Maria Violaris was explaining the same thing to me, because we were seeing graduations going, and I was seeing the flowers. What are these flowers about? Yeah, long tradition.
Yeah. It was very bizarre to me that would happen. I like it, and it's kind of indicative of the traditions that exist there and their ability to hand them down quite quickly, because it's not like people get trained for life to do this kind of thing. It's for a 5-year period or something, or 3 to 5 year period, that people engage with those kinds of things, but people go along with it and they enjoy it, I think, for the most part. I mean, there might be some.
You say one of the things that attracted you to Oxford was this idea that there are many Everettians there, and you'd been learning about Everettian quantum theory. And recently, when I've been speaking about quantum theory and trying to explain where we're coming from on this, I'm saying, look, well, all of these, if you're learning quantum theory for the first time, all of these so-called interpretations are going to sound crazy. So it's almost like pick your crazy.
Yeah.
But when you say Everettian quantum theory, it actually disguises something really important, because normally people just blurt out the thing, and there are two other ways of explaining what this Everettian quantum theory is. So I think it's a nice, neat, formal way almost of leading people down the pathway before you actually spell out what the true explanation is. So why don't you, because no doubt at least some large proportion of the audience here is going to already know what we're talking about, but do you want to just give me a sketch outline? What do we mean by Everettian quantum theory?
Right, so there's conventional quantum theory, which basically has two ways in which you describe the evolution of a system. So generally in physics, you're interested in how do things evolve. So you have a description of a physical system and it takes a certain form, and then you ask questions like, okay, now what will it do a moment from now, a minute from now, or something like that. And in quantum theory, again, conventional quantum theory offers two different, hard to reconcile ways in which a system can evolve. The first one, which is the nicest one, is called unitary evolution, which is just evolution as it should happen according to the fundamental equations of quantum mechanics. So, for example, the Schrödinger equation, which most people have heard of, will tell you how the system should evolve. And when it evolves according to the Schrödinger equation, it evolves unitarily. And that is where most of the explanatory power of the theory resides. So you want to explain, explain quantum computation, you want to explain things like interference phenomena, then you're going to have to use the unitary part of quantum theory and then kind of paste it on top of that with a bunch of clunky rules is a second way in which a system can evolve, and that's called measurement. And when a system is measured, it collapses into a specific state. So sometimes the system can be in multiple states at the same time. Qubit can be up or down. Particle can be in two positions at the same time. And then when you measure it, it collapses into one of those possible states. And that is not evolution as it's described by the Schrödinger equation or anything like that. It seems to be an entirely different kind of evolution that happens under dubious circumstances that are never really made explicit. It doesn't, in conventional quantum theory, there's no theory of what measurement is. It's a thing.
So correct me if I'm wrong before we go a little bit further. This measurement version is saying that the system will collapse into one of two possible states. But are you saying the unitary way of understanding quantum mechanics is that these are not possible states, but given a particular state at some time t, at some further time into the future, they're not possible states, but they are actual states?
Yes. So the thing that Everettians like myself like to do is we just take the formalism of quantum mechanics actually seriously as an explanation of the world. And the most straightforward way to do that is just to say, well, for example, when a particle is described as being in two places at the same time, it really is in two places at the same time. There really are multiple instances of the particle in both locations. And so, as you said, it's not just they're possible locations, or that it's not just that our knowledge of the system is lacking. They actually are in both locations at the same time. And the thing that Everett discovered, which is really a beautiful idea, is that you can explain this idea of measurement, which again in the conventional theory is not defined. It's a very arbitrary thing, as another unitary process. So it's like you can explain measurement using stuff like the Schrödinger equation again.
Right.
So, for example, when you have the particle in the two positions, you measure its position, and then the unitary version of quantum theory says one version of you ends up seeing the particle in one location, another version of you ends up seeing the particle in another location, and that way you avoid all of the awkwardness of conventional quantum theory.
So if we try to observe some particle, let's call it an electron, and try and isolate it at a point, we want to see where it is right now, then there are these laws, correct me if I'm wrong, rules, if you like, about quantum theory, perhaps Heisenberg's uncertainty principle, that because we've now isolated this thing at a particular point, what's going to happen in the future is uncertain in some sense, that it has a range of different momenta. So what's going to happen in the future is it could go off in a number of different directions with a number of different velocities, speeds. And what you're saying is that it really does go off in all these different directions, following many different trajectories at the same time. Okay, so what's controversial about this then?
Yeah, good question. I wish I understood that better. I think, well, the main criticism tends to be it's too extravagant or something. It just can't be that we live in a world that's branching. That, I think there's a quote in David Wallace's book on the topic where it might be C.S. Lewis or something, who says, I can't refute an incredulous stare. Like that's, you can't really do much with that.
Yes.
So that, in my experience anyway, that's one of the main things that people, they just find it's not that it's logically incoherent, it's just too implausible to be true, because we look around us and we see a single universe, and why
it doesn't look like it's quantum. I think, again, in Wallace's book at the beginning, he may quote Wittgenstein, of all the people to quote, but this is actually a good line from Wittgenstein. He said something like, what would it look like? You know, Wittgenstein talking about heliocentrism versus geocentrism. He just asked the question, what would it look like if the Earth went around the sun? So what would reality look like if it was indeed quantum at the emergent scale? Just as it does.
Yeah, that's what you think, yeah. So it's, people have slightly more refined versions of criticisms, perhaps slightly too technical for here, but my impression of them is that most of them have been answered quite thoroughly in the last 2 decades, 3 decades, or something like that, with the emergence of something called decoherence theory, which is roughly the idea that the effects of quantum interference, which is kind of how we know that there's one of the main indicators of quantum theory, one of them big pieces of evidence. So, for example, the double slit experiment, where you send a particle through 2 slits, and then you can see even with a single particle, that's the beauty of it, you can see an interference pattern appear on a screen at the other end of the 2 slits, just by sending through one particle at a time. So you send one particle through, see a dot on the screen behind it, another dot on the screen. You do that many times and you see an interference pattern with certain places where the particle never arrives and certain places where it arrives very often. We have the theory of when that effect is suppressed, and it turns out it's suppressed, so quantum interference is barely noticeable when a system is interacting very much with an environment. So, like, for example, if you have an atom and a photon is constantly hitting the atom, then it's going to be hard for that atom to interfere with other versions of itself. Mm-hmm. And of course, we are being hit by photons all the time. Like, there's orders of magnitude, must be 10 to the 20 photons or something like that hitting us every second. I could be wrong with that. That would be like my estimate. And yeah, so that means that objects like us are constantly experiencing these interactions, which makes it hard for us to interfere with other versions of ourselves, which is why we can't see them. So that, I think that theory, which is a really important addition to the original construction that Everett made, answers a lot of the questions that remained after the work was first presented, and that, for me, really seals the deal. So I think of the questions that still remain, decoherence theory really solves all of it.
And is this related to something you're working on at the moment? Let's just dive into that. What are you working on at the moment? What problem has really grabbed your attention? Whether it's in quantum theory or something closely associated to quantum theory. What are you thinking of publishing soon?
So I have a couple of papers. One of them was a paper with Simone Riefek, who is also part of Conjecture Institute. We'll shout out to him. And we wrote a paper about time in quantum theory and how to measure time. And then besides that, I am interested in a topic called locality, local realism, as it's also called. And local realism is typically thought, so local realism is the idea that there is a real world out there, and the world consists of subsystems, subparts. So like, what would be a good example? If you have a bunch of objects on the table, like a cup and a plate or something, well, then you can describe the cup and the plate and the table independently of each other. And if you want to describe all of them together, then you just describe the cup, the table, and the plate independently, and that gives you a full description of that collection of things. And also, if you do something to the plate or to the cup without without involving the other objects, then the description of those other objects is also unchanged. So that in a nutshell is local realism.
But for some reason, again, correct me if I'm wrong, there's a sense in which what you've just said seems like prosaic common sense, but it seems that this is controversial in a deep way in the physics community. What about that is controversial?
Yes. Yeah, so it is. So there's a long history of this. It kind of starts with Newton, where Newtonian gravity already violates some of the properties that we want from a local world. So, for example, if you move around an object here, some mass, something like the Earth is spinning around, that in Newtonian gravity, that immediately affects something on the other side of the galaxy, like instantly, because there's instantaneous effects in Newtonian gravity.
Why should that be a problem? Again, if you're coming to this completely naively, you don't have a physics degree, why can't we affect things instantly? What's the problem there?
Yeah, so logically, it's not that it's impossible, but it is a problem within Newtonian mechanics, because Newtonian mechanics has two ways in which things can interact. One of them is by push and pull. So you have two objects, and maybe they hit against each other, they have some momentum, and then they push each other away. And those kinds of interactions are all local, so they all happen at a point. Things have to be coincident for that to occur. And that's what Newton's clockwork universe was really all about. So I think it was a clockwork universe in the sense that all the little cogs and gears in the universe, or in the clockwork, can only affect each other by pushing nearby cogs and gears, and then that effect would trickle through the clockwork mechanism to affect other distant parts of it. So that's one way in which things can interact in Newtonian mechanics. And then the other way in which they can interact is instantaneously. So that's not at all like the clockwork. It's like something can reach out to infinity, or to a very far location, and instantly affect it. So that is, I think that is a philosophical problem was a philosophical problem within Newtonian gravity.
Yes, and so when obviously that was replaced by Einstein, improved with general relativity, essentially that problem was solved because we've refuted Newtonian gravity. However, when we turn to quantum theory now, people do talk about this. I think Einstein coined the term spooky action at a distance because it was not understood at that time what was going on. But people today still point at this so-called spooky action at a distance involved in phenomena like entanglement. So this is where you're talking about the important replacement of this local realism within the framework of quantum theory to answer those critics who say, hey, entanglement can only be explained by faster than light or instantaneous messaging across long distances. Is that right? And do you want to flesh that out a little more?
Yes. Yeah. So as you said, in quantum theory, it's now thought that local realism can't hold, that things can affect. So if you do something to a system here, to a particle or something that's entangled with something else very far away, then there's an instantaneous effect on the other particle, even if it's not that the other person, like if someone were with the other particle and was about to observe it, it couldn't tell any there being anything different at that particle just from what he can observe locally. But you will know here that something has changed over there. That's the view people have of it. That's that you can have some imperceptible but real change in another physical system just because of something you do at this location. And it's problematic because, well, for one thing, general relativity does not have this property, and one of the reasons we wanted that theory was because it replaced Newtonian mechanics, which had the problematic feature that they did have spooky action at a distance, as Einstein so nicely and derogatorily called it. But if quantum theory has it, if quantum theory has this spooky action, well then space-time is shaped by the matter inside it. The matter inside it can affect other matter at a distance. So then space-time again has spooky action as well. So it's like it will infect general relativity with its...
Because there's only one reality, so we can't go having one law working over here and another law working over there.
Exactly, yeah. That's exactly it. And so I think Everettian quantum theory very nicely resolves this because of two things. First is things can. So if you have the particle, so let's say you have two agents, Alice and Bob. One of them is over here, one of them is over there. There's a very large distance between them, and they're in possession of a particle entangled with the one that the other one has. And for example, Alice measures her particle, and then she splits. So like there's now two Alices, and one of them saw one outcome, the other one saw another outcome, and Bob does the same thing. He splits, and he saw both outcomes that were possible. And what now ends up happening is when they meet, only certain versions of them see versions of the other one, and that establishes correlations which otherwise have to be explained with non-locality. So usually you would have to say, well, I saw a 1 because Bob's qubit is also immediately a 1, or something like that. But in Everettian quantum theory, what you can say is there are two versions of each of them, and there is no fact of the matter about what the other one observed before they meet up. But we know that if they were to meet up, like for example, it could be that if this is the Alice who saw 1 and this is the Bob who saw 1, that only they can see each other, so only they can interact. If Alice tries to see the other Bob, she just doesn't. She will pass right through him. If they try to write each other a message or something, they just cannot communicate with one another. So you get these correlations between like Bob who saw 1 and Alice who saw 1, Bob who saw a -1 and Alice who saw a -1, just through local rules. So they want to meet up, but some versions of them are invisible to versions of the other one. And that allows you to explain why these strange correlations can happen between systems that are distant from one another initially through entanglement. Whereas again, the usual story would say, well, the correlations happen because there is an instantaneous change at the other side. And here we can say, No, it's just like the way that things can interact in the multiverse is such that sometimes you're just invisible to someone in a weird way.
I think that's clear, but I fear that in the popular zeitgeist we are going to have to deal with faster than light communication because of quantum theory for some years to come, in the same way that we have to deal with consciousness plays a fundamental role somehow at the fundamental level of quantum theory as well. We've been dealing with that for decades as well. What else at the moment are you working on professionally aside from that paper that you've talked about?
I'm trying to generalize these things. So there's a very nice formalism by Paul Raymond-Robichaud, another fellow, and
I think he may be in the chat, but I'm not sure. There is a Paul there.
So he has a very nice formalism which captures what it means for a theory to be local, not just in quantum theory, but just for anything, any possible theory that we could think of. If that theory is local, it has to have certain constraints, and Paul axiomatized those constraints. And one of the things I would like to do is to capture more rigorously these properties of entanglement, where David has a nice term for it. He called it locally inaccessible information. So there's some kind of information you can store in a quantum system, just like we did with the versions of Alice and Bob, who branched locally, where you can't see that information locally. Like, for example, Alice cannot see which version of Bob she's going to interact with just from observing her qubit. But when she meets up with him, that information is revealed. So she needs this other system, she needs Bob, to reveal something about her own state of affairs, her own physical description. And yeah, I'm hoping to generalize that. I'm also working on a textbook on quantum theory.
Well, tell us a little bit about that. And by the way, yes, Paul is indeed in the chat there. We'll be speaking to him in one of these interviews at some point in the future as well. And we can delve more deeply into local realism everywhere. But on your textbook, what is special about this particular? There's a lot of quantum physics textbooks out there, but you're writing something that is rather unique as far as I understand. Can you tell us a little bit about it?
Well, the thing that we hope to do is to, first of all, write a textbook which is about Everettian quantum theory. So it's unlike almost every textbook that I'm aware of, except again maybe David Wallace's book, which is not. So David Wallace wrote an amazing book, but that's really for postgraduates, or it's a text for someone who has already some technical capacity in physics and mathematics. Whereas we hope to write something that is manageable for anyone who is interested in the topic, not specifically people who are already have a technical background. And so it's going to be Everettian, it's going to be the local account of quantum theory, and we hope to avoid what we consider to be many of the pitfalls of the conventional approaches. And to be actually explanatory, to actually say, well, there is an explanation for this stuff that is going on in quantum theory, which is one of the two main pillars, really, of modern physics.
And as I understand it, it will contain mathematics, but unlike, I know that when I went through, as no doubt you did, through a physics degree, it was just solving equation after equation, doing exercise after exercise in tutorials and working through proofs during the lectures and lots of calculus and that kind of thing. But I think that you're not going to go down the Schrödinger picture quite so much, so it won't be solving a whole bunch of differential equations and that kind of thing, but you're going to be using a matrix style approach. Is this right?
Yeah, so for quantum theory to be local, one of the things you can do is to express it in this thing called the Heisenberg picture, which is a description in which you're keeping track of the observables of a system. That's already a little bit technical maybe, but these are you can represent them as matrices. It's maybe even more pure to think about them as just mathematical objects that have a lot of similarities with conventional numbers, but which violate the assumption that, for example, that they're multiplication commutes. So they are, in Dirac's terminology, they're Q numbers, quantum numbers. And it is often very elucidating to express quantum theory in that framework. So we hope to do that generally.
And when you say we hope to do that, this is yourself and David Deutsch, and without, breaching anyone's privacy or anything, I think it'd be really interesting for the audience to know, because over the years there have been some great scientists, great thinkers, people would like to have known what was it like to actually work alongside someone like Feynman, let's say. What was it like to have met Schrödinger? You're working with David Deutsch. Can you give us a little insight into what's it like? You've authored a paper with David Deutsch, or you're writing a textbook with him. Is there something special you can tell us about just having David Deutsch as a colleague?
Well, he's a very friendly chap. It's just very nice to talk with him. And I think the main thing is that there are lots of very nice and fun discussions and discussions about topics that are actually, they matter. Like, if there is some problem in physics, don't know how to convey this, but I often find that people in my field need some effort to be persuaded that there is a certain conceptual issue somewhere. If you say, well, okay, we could, for example, maybe you can program something, or maybe I have this with AI, that we have these AIs and they can do certain things, but how can they do them? What is it like? How can it be that the AI has a certain skill? What mechanism is the AI using in its software to perform some task? Something like that. I've often had it that people would reply with something like, well, it doesn't matter because we've already made them. So what's the point in asking that? Yes. We know everything we need to know because we can produce these things. So what's the point in investigating that kind of thing? And what I've noticed with David is that those are exactly the kinds of things he's interested in. So it's exactly those kinds of questions, the conceptual questions, that are important to him and to me as well. And that's extremely refreshing every time. Yes. So, and yeah, you will just, besides that, it's all to have a conversation with someone where often they say something that is very worldview changing, so that like refreshing worldviews or refreshing ideas are,
and then can provide reasons and argument in such a clear manner, because again, this comes back to the textbook that you're writing, which is what I'm really looking forward to. In the same way that we all read textbooks, especially in physics, where there were just questions left unanswered, not necessarily because it is an open question in science, but simply because the author just didn't bother thinking that it was important to flesh this particular thing out or explain this thing, or perhaps thought there was no such explanation, and just a lack of clarity there, and the books were dry. In that same way that often when you read a popular science account of whatever it happens to be, you're bamboozled by a whole bunch of jargon, which is why The Fabric of Reality and the Beginning of Infinity was so refreshing. It's written in such a clear way. At least I found it exceedingly clear. And so that's what I would be looking forward to in a textbook that you and Dave would be writing, is that it's going to be expressed in a way, I imagine, that is going to focus on the explanations rather than just, here's yet a mathematical proof of this particular theorem, or here's another, we're just describing what happened in a particular experiment rather than explaining why this particular thing is happening.
Yes. Yeah, and as Paul would say, so Paul is a mathematician by training. That way of doing mathematics is also just wrong. You can't really do mathematics and physics that way. It has to have an explanation for you to understand the assumptions that you're using, the reason why the equations hold, stuff like that is all important to actually doing the mathematics as well. So I feel like without focusing on the explanations, the actual structure of the theory also just does not make sense. Like, as I keep saying, there's no conventional quantum theory doesn't come with an explanation of what measurement is. It's just a thing that is invoked, and it's not clear where it's coming from. It's not clear where it's happening. It's not clear what's doing it, and that should be considered a severe issue in how you formulate the theory. If you have components of the theory which lack a precise formal definition, but then you want to make it like a rigorous mathematical framework, you can't have both. You can't have something which is imprecise, but also want it to be a solid mathematical framework, which of course it should be. So that is, yeah, it's very strange to see that is missing from modern physics, because you would think that is the thing we all care about. That's all. It's the thing we want. But yeah, by downplaying the importance of explanations, you also, I would almost say destroy, but maybe that's too strong a term. But you are making the other parts of the theory worse too by downplaying the explanatory part. Both the mathematical framework suffers from that, and I think even your ability to predict stuff suffers from that. But my main concern would be with the mathematics. The mathematics already immediately suffers from a lack of interest in the actual explanatory power, the explanatory framework of the theory.
When people think of fundamental physics or the foundations of physics who aren't necessarily working in the area, but they might, just be interested in science generally, I think they will naturally think of, well, the central problem here is the unification of quantum mechanics and general relativity to try and figure out the theory that is beneath it all. And attempts have been made, such as string theory and loop quantum gravity. You're coming at things a little differently, I think. But could you tell us a little bit about let's start with what the problem is. Why is this a problem at all in the first place? Who cares about whether or not general relativity and quantum mechanics need to be united? What's the scientific problem there? And what approaches have been tried so far? I've mentioned two, but you may know of more.
Well, so the way I always see it is that in general relativity, you have space-time. You have a general description of space-time, and its shape is determined by the matter inside of it. So the matter and energy inside space-time determine the shape of space-time, determine its curvature. And the actual matter inside space-time is described by quantum theory, which is not a thing it really allows for. So in the way that we think about general relativity, you kind of have to assume that matter, for example, has a definite position. When you don't, you assume that there's some expectation value for it. But anyway, the main thing is in general relativity, it doesn't allow for matter to have two values at the same time. But
so when you say the Earth is at a particular place, you mean the center of the Earth can be isolated at a very precise point, and it's there.
Yes, exactly. Yes, so it should have a definite location within general relativity for it to make sense. And
most people would think, well, that of course makes sense. It wouldn't. Common sense would say, what could it possibly mean for the center of the Earth to have a range of locations?
Yes, but it does. It does have a range of locations because The Earth is made of atoms, and atoms are quantum systems, and quantum systems tend to branch. So in different parts of the multiverse, the Earth will have a very slightly different position, or maybe a radically different position, depending on its interactions with other systems. Like maybe in some part of the multiverse there was an asteroid that severely knocked the Earth off its course, or something like that. At any rate, all we need is that matter can have different positions at the same time. Even particles, even for small particles, this is already a problem. And we know that small particles, it's not controversial to say that an atom can be in two places at once. But even an atom being in two places at once, an atom has some mass and therefore will deform space-time, however slightly. And the issue there is that space-time can only respond to the atom being in one location. So if it's in two locations at the same time, it doesn't know what to do. And that would make you think perhaps space-time should also, like the atom, be able to assume multiple values at the same time. So maybe when the atom is in one location, or when the Earth is in one location, space-time is curved there. And when it's in another location, it's curved there. And when it's in both locations, then, well, in some part of the multiverse, the space-time is curved one way, and in one part of the multiverse, it's curved another way. But that description that I just alluded to doesn't exist. So there's no, we don't have that, oh, in one part of the multiverse, there is this space-time, and in another part, there's another space-time. That's not a thing you can say. So that's the reason why we want it, because, yeah, we have these two conflicting stories about what's going on.
So that's fascinating. I think that's a very clear elucidation of the problem that we have. So therefore, most people, again, who are not professional physicists, they will have heard, oh, string theory is an attempt to unify these two. Does it go any distance to solving that problem that you've just talked about? And if not, what is it doing?
I don't actually know that much about string theory. From what I understand, people claim that it does do that you can provide such a description, but not in any way that I understand. So I can't. The kinds of questions, I think for me with string theory, the kinds of questions that I'm interested in are not being answered by them. And if they are, they're not being answered in a way that I find comprehensible. Yeah, sometimes I have a friend who used to be a string theorist, and he claims
Eric Marcus?
Yes, that's right. So Eric Marcus sometimes claims that like I would pose problems like this to him, no, that is solved, or there is an answer to that question. But I don't know. I think the actual progress that we've made in that direction, as far as I can tell, is not reflected by string theory. If someone disagrees with that, I'm very curious to why I'm wrong on that topic. But yeah, we have, for example, simple theories, but very important theories of time in quantum theory, which go some way towards explaining this. They haven't yet managed to actually get the superposition of spacetimes or anything like that. But that's what it's going towards. That's the kind of thing you can see a glimpse of in those models. And something that I've always wanted to see in string theory is these kinds of constructions worked out in the same way, but I've never been able to find it. So, yeah.
Yes, I don't know much at all about string theory beyond the fact that it exists. and loop quantum gravity is one that comes up as well, Lee Smolin's idea. Do you know anything about that? And again, whether or not it's gone any distance to solving this particular problem?
No. I'm not too familiar. I know that it is a thing which people think is very important, just like with string theory, and I don't know that much about it, I'm afraid. I think with both people, the one thing that I think is important with string theory, which I disagree with, is that it starts from a very classical point of view. So that you're always quantizing certain classical quantities, and then you get a string theory. And that, I don't think that is how we're going to get something like a quantum theory of gravity. It's too much. David has a very nice article about this, where what was the analogy he had? I think is it called phlogiston, the theory of phlogiston.
Phlogiston, yes.
Which is supposedly explains, why certain materials can burn and why others can't, and it's he says our current theory of, for example, quantum fields and string theory and those kinds of things. I'm not sure string theory is mentioned in the article, but I think it applies to it as well. It's a little bit like saying we take a theory of phlogiston and then we dephlogistionize it by saying, well, there's this thing called combustion, and we're going to replace things in a very mechanical way. But it doesn't, why would that work? That what you want is an explanation of how the world is, rather than say, here's a cookbook recipe for getting from your classical theory to your quantum one. And I also think that I agree that is a very strange method of doing science, of saying, we have a classical system, and now we're going to do this little ritual that we always do, which worked for some reason, and now we're going to hope it works again for some unknown reason. And that's roughly how string theory is done. That's how quantum field theory in general is done. And I don't see how that could be satisfactory.
And is that similar to the idea that, well, we've got these, call them three fundamental forces, electromagnetism mediated by the photon. We've got the weak nuclear force, we've got the strong nuclear force, each of which are mediated by these bosons, the particles. Why wouldn't a solution be to look for the graviton? And once we have the graviton, then we will have the particle that mediates the force of gravity. Could that be a solution? You see this floating around in popular accounts as well?
I think that's been tried and been found insufficient. The explanation of the other forces is also it's a very good explanation in some ways, and in other ways it's a very bizarre explanation because of the various singularities that we have in those theories. So this thing, quantum field theory, which is the underpinning of our modern understanding of forces, is a somewhat problematic theory because it basically tells us there is a scale at which it no longer applies. We can use it as an approximation to high accuracy, but we know that it's not really capturing the microscopic physics. There is a scale, if you go too deeply into the theory, you just get infinities, and you have to kind of cut that out or average over that. And we know that if you ignore whatever is going on at the very microscopic level, the thing that is described, presumably there is a theory beyond quantum field theory that actually describes the extreme microscopic details of reality, not captured by our current understanding of quantum field theory, in such a way that this underlying description doesn't always matter. So my favorite example of this is in classical physics is fluids. So in fluid dynamics, in classical fluid dynamics, you can assume that a fluid is a completely continuous thing, and that works very well for certain circumstances.
And by continuous thing, you mean not made out of particles. Exactly,
yeah. So it's infinitely divisible, it's completely smooth, and that's a good explanation in certain cases, but it fails to be a good explanation whenever the size of an atom is relevant to some phenomena. So a very simple example is a droplet formation. So you have a liquid, main body of liquid, and then there's some droplet forming and it's still attached to the rest of the liquid. And what has to happen is that there's like this very slim strand, right? This very narrow strand of water attaching the droplet to the main body, and that has to get narrower and narrower until it breaks off, because at some point the droplet has to become an actual droplet and be independent of the main body. So there has to be the strand that becomes extremely thin. In the real world, what happens is it becomes so thin it's only a couple of atoms wide, and then it just, the atoms are no longer attached to it, like they don't attract each other sufficiently anymore, so they just float off. In the continuum theory, that doesn't happen. What happens is you get a singularity, because the width of this thing goes to 0, and it becomes like a spike. It becomes a discontinuity. And that's a case where you can see like the microscopic physics is understood now, is the theory of atoms. The theory of atoms tells us what's going on with the liquid. And the continuum theory, the theory of classical fluids that we had, was insufficient because it doesn't actually capture that there is such a thing as an atom, and that's going to be a problem whenever the size of an atom is important to something going on in physical reality. And probably, like, we expect that the same thing is true with things like quantum field theory more generally, that quantum field theory is also a continuum theory, and it's neglecting whatever is going on at the more microscopic level, for which we don't have a theory. So like what we have for the fluid case is the atomic theory, and that is what's lacking at the moment for quantum field theory, where we don't have an explanation of these more microscopic phenomena. So they're extremely small, by the way, because of course quantum field theory is already a theory of extremely small things, but this is even smaller than that.
Mm-hmm. So we've discussed I wouldn't want to call them dead ends necessarily, but attempts that have been tried but have not so far been successful to make progress in fundamental physics. And you're working on something that we hope can make some groundbreaking attempts to make inroads into a whole bunch of different areas. Could you tell us a little bit about that? I think people know what I'm alluding to.
Maybe I don't.
Constructor theory. I think that this new attempt to hopefully make progress in fundamental physics that's different to what has been tried before.
Yes. So constructor theory is a theory about which tasks are so first of all, conventionally in physics, what you do is you have some equations of motion. You have some equations which tell you how a system evolves through time, and then given some initial conditions, you can predict the state of a system at a later time, and that is insufficient for explaining certain phenomena, like information, for example. It's one of these things which information is something that doesn't just depend on what is actually going on. It depends also on the things that could be made to happen. So if I hold up a flag and the flag has a certain color, say it's red, then the reason that could be information, I could be signaling something to you. It could also be that it isn't information, because there's no way for me to make a flag that's a different color. If I can only ever hold up a red flag, if the only flags that existed for whatever reason in this imaginary universe were red flags, then I could never tell you anything with a red flag, because you don't know, there's no other state it could ever be in. If I try to tell you whether I'm doing well or badly or something, well, I can't. I need at least two different states to communicate that with. So sometimes what's actually going on is not sufficient to explain the world. We also want an explanation of what could be made to happen in the same circumstance if, for example, we had different initial conditions or something like that. And that's what constructor theory provides. So constructor theory is a theory not just about, or it's not a theory about what actually happens. It's a theory about the things that can be made to happen. It's a theory about possible and impossible tasks. And yeah, I very much like the theory. I think it has great potential and has already explained enormously important things. And my favorite example of that is that it is able to explain comprehensively and precisely what information is in a way that conventional theories of physics just can't by their very nature.
And if anyone wants a popular account of that, Chiara Mailetto's brilliant The Science of Can and Can't actually has quite detailed chapters devoted specifically to information, quantum information. I think she talks about just what you've mentioned there, that an information media needs to be able to allow for the flip operation that you've just talked about. So the red flag needs to also be able to turn green or something in order for it to be an information medium. And copy, I think, is the other property that information media. But that's an excellent book for anyone who wants a popular introduction to constructor theory and its potential to cover everything from the foundations of physics, even into epistemology and biology as well.
Yes.
I might just take the opportunity here. I'll ask a few more just fun questions, and then we'll go to the audience as well. And this may actually invoke something to do with constructor theory or not. When people become fascinated by physics, they encounter all sorts of equations, but none of them have quite the amount of mystery or intrigue associated with them as the one I'll mention. No one thinks of something like, although, you know, as physicists we might think of things like Maxwell's equations are indeed interesting. No one goes thinking that there's something truly intriguing about Ohm's law or something like that. But the second law of thermodynamics holds a special place in physics and is often held up as something that stands apart from just about everything else. Can you tell us a little bit about what is this second law of thermodynamics and or what is so mysterious about it?
Yes. Second law of thermodynamics it's not conservation of heat, it's thermodynamics, it's entropy, I assume. So the strange thing about it is that it seems to break a certain symmetry that we see in the usual dynamical equations. So generally, the fundamental equations of motion are time reversal symmetric. So they tell us that if something happens one way, then it happening in, so for example, if you drop a cup, then the motion of the atoms in the cup as it breaks is they cover a certain path, and the fundamental equations of physics tell us that the reverse path is also physically possible. And that seems very odd, because things like cups reassembling doesn't happen in the world. So we see cups falling apart, we don't see them reassemble themselves spontaneously. And our current theory of thermodynamics seems to suggest that that should be the case, that there is this fundamental asymmetry in the world where entropy is increasing, and in a way that provides an arrow of time, whereas the fundamental equations don't seem to have that. They don't seem to have this arrow of time built into them. Julian Barber has a very beautiful explanation of this. I don't know if have you heard it, the Janus point theory?
Yes. Yeah, there's a book. You wrote a book, yes.
Yes. Yeah, also called the Janus point. And one of his solutions was to say, that perhaps what's going on at the fundamental level is that there really are, like, there's a point of lowest entropy, and then, or I think he would call it complexity, and then in both directions from that point, complexity emerges. So if you run it backwards and you run it forwards, complexity emerges in both directions of time. So it's like each of those directions is its own arrow of time. So there's an arrow of time going that way and an arrow of time going that way. And that is one way of resolving the apparent paradox that there should be an arrow of time in the universe, whereas the fundamental equations of motion don't allow for that. Then it's apparently something Boltzmann already kind of thought of. So the thing Boltzmann thought of was that he imagined the universe being complete thermodynamic equilibrium. So there would be no further work or anything could be done. And he then imagined, well, maybe there's just statistical fluctuations in, for example, things like the entropy. So maybe for just purely statistical reasons, the entropy is constant, but then it dips suddenly. So there's a little dip in the entropy. And he said, well, then in one direction, you would see lots of things emerge, like you would see an increase in entropy from its lowest point to something higher again. And maybe that's us. But the same is true of the other direction. So he already thought that, like, in the dip itself is symmetric. So you can also, in the other direction, entropy is increasing. That is quite, I didn't realize he thought this until I read Julian's book. It's quite an ingenious solution. It still doesn't work in the Boltzmann's case. And Julian makes it more plausible. And then constructor theory has yet another possible solution to this, which is to say that although the dynamical equations are indeed time reversal symmetric, certain tasks are not. So it could be that there is a task which you can only do in one direction and not in another, even though the equations of motion are reversal symmetric. Where a task is saying, okay, you have a certain input state and you want to reliably produce another output state. Maria Violaris and Chiara Miletto had examples of this in their work, which is, so there's all these, it's not a topic that I necessarily work on, but I see lots of very nice guesses at what it is that could be happening here. And I don't.
Yeah, and shout out to Julian Barber as well. People are often asking me, what books to read. They've read The Fabric of Reality, The Beginning of Infinity, they've read Popper. Grab a hold of Julian Barber's The End of Time, that's his first book, and also The Janus Point for more about that. And also to Chiara Miletto, of course, you've just mentioned, I think that the paper may have been called The Constructor Theory of Thermodynamics or Constructor Theory. I can't remember. There's
mentioned in there, she mentions this property in that paper. And there's a kind of proof of concept with that she worked on with Maria Violaris, which I think is called the quantum homogenizer. And that's work that appeared a couple of years ago, which again is this idea that it's a very nice idea. It's a very nice idea to again, you want to abstract away or not think too much about the actual equations of motion. You want to think about the things that you can do, and the things that you can do one way. So like, I think their standard example is something like, you can build a constructor for whisking eggs. Like you can have a whisk and you can whisk the eggs, and then you have whisked eggs, you have some destroyed eggs in a cup. There's no constructor for doing that the other way around. That's the claim. So even though the universe is indeed time reversal symmetric, that doesn't mean that there is a constructor that performs the task the other way around, which is very odd. It still kind of boggles the mind that that is the case, but it's a nice idea. It's very pretty.
Yeah, it's a very nice idea, and it sort of suggests taking the theory seriously, as we should. We presume that these things called constructors are in some sense fundamental, and if they are truly fundamental, then they're deeper than what the equations of motion might suggest, because although the equations of motion suggest that we can just have this time reversal where we could whisk the eggs and we get a fully formed egg at the end of the whisking, there's no such constructor, and the constructor may very well be deeper. So that's fantastic. Now I'm going to shift gears entirely and move into an area that's not your every expertise, but then again, it is the area of no one's expertise. But it's just something that people like to ask smart scientists now and again. The Fermi paradox. Where are they? Where are the aliens? Sam, what are your thoughts on this? Why haven't we been visited yet? Because the cosmos is so vast, and presumably the laws of the evolution of life are universal. So can you provide any thoughts on this?
I don't know. I think that well, it's weird because we lack any explanation at all about how life began and what kinds of circumstances are necessary for it, and that's kind of inherent in the. Like, I've had arguments with people about this topic, about like what kinds of things do we need for life to begin. And we don't know. We don't know the kinds of environments that could possibly give rise to life, because life is a thing that creates knowledge. It kind of creates its own ability to survive in an environment. Like sometimes people say, well, you need a sun, right? You need to have a planet that's orbiting a sun. That's not clear, because it could be that they use geothermal energy. That's another way of getting energy. You're sure you need energy, but that doesn't mean you need to get it from a sun. So that's one thing. So it could be that life. Well, the thing I often hear people say is life is just very unlikely to begin anywhere, and then that we don't know the probabilities of that. We don't know from fundamental theories. We can't derive that yet, if at all. Maybe that's not possible at all. And I honestly don't have a good answer. I think it is a bizarre thing the more you think about it. Like, life is a thing which, by its nature, is exponentially increasing. So by the time that we're here, we should have expected others as well. It's true. I don't know. Yeah, I don't have a good...
It's an astounding mystery, I find, because on the one hand, it appears as though on this planet at least, life arose as soon as it seemed to have been able to chemically, once the Earth cooled down, sort of 3.8 billion years ago, there's evidence that the early forms of life seem to have appeared. So as soon as the conditions became even moderately friendly, that there it appeared. But then scientists in the lab doing Miller-Urey type experiments don't seem to be able to replicate this. So they seem to be, the failure of those experiments seem to suggest it's difficult. So on the one hand, we've got an indication it's easy, and that's coming from the other angle, it seems to be hard. But as you say, maybe you need an energy source, but not necessarily a star, because the earliest forms of life thermophilic, and so they like warmth, but perhaps near the center of, I don't know, the Pluto, you might very well have nascent bacteria because it's warm enough in the center of Pluto to have life. But yeah, it is an enduring mystery. Okay.
It's very strange. It's and as I said, like, even the phrase, well, when it became moderately friendly, we don't know that it's moderately friendly relative to what we have now, but that isn't an explanation of the thing that it could have been, right? Like, it could have been something other than carbon based, or maybe it couldn't have been. We don't know that either. We don't know that carbon is a very nice thing to base life on, because it allows for immense variety, but that doesn't mean it's the only way. But it also doesn't mean that we don't know from first principles whether it is or isn't the only way. It could be that other forms of life basing life on anything but carbon means it's not going to have the variety necessary for adaptation and evolution to happen. But maybe there are other ways, and even that we don't know. So I think what we would need is, well, first of all, some kind of theory about the kinds of ways life could get started, or something like that, or an understanding of even as I say that, I don't know if that's true. I just know that is another problem, that whenever you want to make a claim, whenever people talk about the Goldilocks zone or something like that, you go, well, that's all based on the very parochial assumption that life has to be like life on Earth, which it may or may
Yes.
not be. So that doesn't really help. That just makes it more mysterious.
It's almost as if you're saying that this fashionable idea that we're near the end of science and discovering everything that is to be known might not even be true.
Yeah.
Now,
yeah.
I might ask a meta question. We're here talking on the Conjecture Institute's live stream for the first time, and the Conjecture Institute is a new initiative, and it's an initiative that has appeared for a particular reason. Now, you've worked in universities, you're working in a university now. We don't want to denigrate universities across the board, but there are issues with conducting pure research within the traditional framework, within the traditional university system. Could you outline what some of those issues might be, just very broadly speaking, for a theoretical physicist or for indeed any scientist who's working within a traditional research institution, and what something like Conjecture Institute can allow for that perhaps a traditional institution doesn't allow for?
I think in traditional institutions, there are several problems. The first one is that for many people, for example, research and teaching obligations go bundled. So if you want to do research, then you have to teach. If you want to teach, then you have to do research. That is something that's fairly inflexible. It's not the case that people can never decouple these things, but generally it's hard. Funding is a thing which is hard. Funding research is hard at the moment. It's more and more the case that people want you to basically have already discovered the thing you're going to try and find out anyway. So if you write some research proposal, then you either have to lie or you have to tell the truth that you do in fact already know what you're going to discover, and that's not good either way. These are issues with research at the moment, with the university structures at the moment, that I'm not sure how to solve. I think there are people who have tried over the years to solve these things. There are initiatives in the UK that try to make fundamental research more easy to fund. But it seems to me like it's on the decline. So funding fundamental research is becoming overall harder in most places, as far as I can tell. And it's a variety of things that are going wrong there, including, well, maybe most importantly, it's taking away power from people who are, for example, leading a research group, in having them make choices about who they work with and who they hire, and having that be replaced with committees. That's another thing that I find very sad. Because if you're the head of a research group, I think it should be up to you how you spend the money and how you try to, who you hire, that kind of thing. That should, leaving that up to a committee almost immediately means that you will have to make concessions that are probably unnecessary. It means that you do not have full control over the candidates you hire, that kind of thing. Those issues are plaguing not just fundamental research, although fundamental research I think is having a particularly hard time because it doesn't have the benefit that I can say, well, in the next couple of years you're going to receive the following payoff from funding this kind of research. It's much more long term than that. So practical research has the benefit that they can say, well, okay, look, we want to do X, Y, Z, and we're going to be able to have some actual usable payoffs within the near future. And that is not a thing you can do with fundamental research, even though in the long term, fundamental research is as, if not more important. Like our theory of electromagnetism was once an issue in fundamental physics only. It was not a thing that was seen as going to be a generator of new technologies and things like that.
Yeah, and so you've mentioned there sort of general administration stuff, the possibility of teaching duties, and I think what you were just alluding to there is what David Deutsch has mentioned before in various places, which is that if you want to get funding for something in a traditional institution, you're going to have to write a proposal. But that, and what your goals in the proposal are going to be, what the outcomes are going to be, but of course specifying the outcome of pure research ahead of time is ridiculous. It actually violates a fundamental epistemological law, which you cannot predict the content of our future theories. You don't know what is going to come out of the research that you're going to have. You might have a very broad goal. I want to make progress in the foundations of quantum theory, but beyond that, you can't specify what you're going to discover.
Yes. Yeah, absolutely.
So
it's bizarre that you're in that situation, that we're all in that situation, that you, as I said, you have to either lie or you have to tell the truth, and it's a very sad truth. There's no point in really doing what you're doing because you really know beforehand what you're going to find. You can say on paper, we expect to find X, Y, Z, and you'll be absolutely right. So that's no way that fundamental research can continue. Again, there's always exceptions. So there's always something which allows that, some grants, some committees which do somehow permit research to go on, but it's unreliable, and it is, and it's still, even then, it's crazy. It's crazy that you have to do things which are logically impossible, or at least epistemologically impossible.
And so Logan, who's the president of Conjecture Institute, and I think we've got Aaron and David there as well on the board, they're not sponsoring projects, so to speak. They're not saying to the fellows, well, this is what we're expecting, after some period of sponsorship, but rather they're sponsoring the person and just saying, go for your life, do your best. You've already demonstrated that you are an intelligent person, creative person, a person who's willing to be interested in solving particular problems, and we don't mind what you're going to do. So looking forward really to what all the fellows actually produce. What I might do now is I'll go to the questions that we have received on X, and I think we've got one on the chat as well. How are you going for time?
Yeah, I'm doing all right. I can keep going.
Good. Okay, so the first one here is from another fellow, Carlos de la Guardia, who has asked, what's a good way for a layman to get into your work, Sam, and your branch of physics more generally?
So I have a blog where I sometimes blog about fundamental physics. That's not very technical. So if you want something that's not very technical, then the blog has some stuff for you there. If you want to get into slightly more technical things, then it starts depending on what exactly it is that you are interested in. If you're interested in, for example, time in physics, I suggest basically anything by Julian Barber, including his book, The Discovery of Dynamics. I've yet to read that in full, but that is an excellent read. There is, of course, David's work. There is, I sometimes watch lectures by Leonard Susskind, who also has a series of books, which I don't really think that there is a quantum book that I recommend. I think all of them have flaws, but his one was nice, modulo not being Everettian. His lectures are also good. They're free on YouTube, so that helps. Feynman lectures. These are not necessarily the things that I'm doing right now. So if you want to do the more specific and the more it is about my research specifically, the less I will be able to give you something to read except for my papers. But then that's going to be too technical maybe.
And your blog, how can we easily find that? Can we just Google your name?
It's a Substack, and I have it on my Twitter.
Okay.
It's linked in my Twitter bio, I believe.
Good. We'll put the link below this video as well anyway.
Cool.
Tybalt has asked, does Sam have ambition? More generally, is it helpful, detrimental, or neutral for a physicist to be ambitious about his work? Interest seems key to learning and creating knowledge. What about ambition? Are you ambitious, Sam?
I don't know. I think I like problems. I think I like problems, and I would even like it if someone were to solve the ones I'm interested in. I wouldn't begrudge that. I would be very happy if someone gave them to me, to the solutions that I want on a golden platter, and I'd like that maybe just as much, although there is the joy of discovery. But for me, the real thing is that there are certain problems, and I care about them, and I would just like them to be solved. And then presumably after they're solved, there's going to be more problems, and then I can work on that. But I don't think, probably I have some, like everyone probably has ambitions, everyone has stuff that they want, but I mainly care about the conceptual issues and wanting solutions for them. Like if someone were to think of, I don't know, a quantum theory of gravity or something that solves the problem that we were talking about earlier, I would be nothing but happy. I would just be glad that the problem is solved, and then we can move on to other problems.
Yeah. Now, no offense to Rohit Singhal, but he's asking a question that is dreaded by everyone who ever creates or publishes anything. I'll ask you anyway, Sam. The question is, when is the quantum mechanics textbook you're working on coming out?
I don't know, and I won't be tied down on when it's going to be done when it's done.
Yes, excellent. LearnPort has asked, what's the best way to learn the basics of physics? Which subjects and content should be studied?
Okay, so I don't think there should be, I really dislike this idea that there is a standard curriculum, just generally. I really do not like it. It kind of gives me a feeling of dread and unease whenever I find out that people assume that there is, and even worse when there actually seems to be something like a standard curriculum across not just different people in the same country, but different people in different countries even. So I don't think there should be such a thing, and I would resist trying to find a standard curriculum. I think the best thing that people have done for me is just advise me good books, just like fun books, and then read the book in whatever order you want, skip anything that doesn't seem interesting enough. Don't spend needless hours studying something that you really do not seem to like just because you think, oh, it's in the book and I have to read it. It's therefore I should go through it. So that would be my first response to all of that. Just don't waste time on things which do not intrinsically interest you. And then other than that, I mean, there are good books. There are nice books, especially like there's the Feynman lectures. I like the Feynman lectures. I also did not read all of the Feynman lectures, but I read a lot of it. And there are several other textbooks. There's mathematics books. I'm going through a bunch of mathematics books myself at the moment, by, for example, Terence Tao, who is brilliant.
Yes, he's a wonderful blog as well, Terence Tao.
Yes, yeah, I've tried to read the blog. I've always, I think I must have picked out the very technical blog posts of his.
It's vast. I mean, yeah, I feel the same way. There are some there that he's clearly speaking to his peers, but you can find the odd nugget there, here and there, where he's pitching at a lower level for mere mortals.
Yeah, I still need that. Yeah, but I like in the textbook that it's an introductory course in real analysis. Which is, I think, also the title of the book, just Real Analysis 1. And it's very good. So those, like, just find cool books. That would be my main thing. And one cool book that I can recommend is the Feynman lectures. Another cool book is Real Analysis by Terence Tao. That kind of thing. That would be the way to go.
And this is a question that I've had over the years as well. What's the best way to learn physics? And I'd always just ask, essentially, what problem are you trying to solve? Why are you learning this physics thing? You know, if the reason is to become a research physicist, then I agree with Sam. It seems absurd the way in which we teach our undergraduates. You know, let's go through 3 years of kind of classical mechanics, solving all these very, very technical issues with like the three-body problem, and you know, way that can become really, really complicated technical mathematics associated with classical mechanics. But of course, no one's making, well, I say no one, there are some small exceptions to this rule, but generally no one's making progress within Newtonian mechanics. If you want to be a research physicist, you want to know what the cutting edge is. So why not start there? Why not start with the area of physics you're interested in? And perhaps these days you could jump straight into constructor theory if you liked, and you know you can almost forget about Newtonian mechanics entirely. So it depends on what you're doing. If you're studying basic physics to be an engineer to ensure that the bridges stay up, well, then that's a different story altogether. Yeah. Eric asks, what, if any, is the connection between Sam's work and constructor theory? We've sort of touched on this.
So the main overlap at the moment is that I am interested in theories of information, particularly the theory that constructor theory, like theory of information that constructor theory provides, is nice, and I would like to use it to explain various things in local realism. And that is really the main connection I have at the moment, that constructor theory just provides a very beautiful way of generalizing, not just beyond the equations of motion, but also beyond even quantum theory and the current theories of physics that we have, what we want from information. What is it that defines a system and an information medium? And I think it's very rich and still allows for more discoveries and more ideas to be made and conceived of, specifically with regards to locality. So specifically, I would like to use it to explain aspects of local realism.
Fantastic. In the same vein, Arya asks, what problems in physics seem interesting and potentially fruitful to you, and what about problems outside of physics?
Within physics, there is the problem of time. There's the problem. There's these problems in locality, as well, as I said. One of my favorite problems at the moment is that we have a theory, we have a description of time in quantum physics, which is provided by Page and Wouters, where essentially what you say is there seems to be, and usually you invoke something called like an external time parameter. You have a system, it's evolving, what's it evolving relative to an external time, like kind of like an imaginary clock that's ticking away somewhere. And Page and Wouters had the brilliant idea, based on an idea of Wheeler's, to say, well, let's just not assume that there is this external clock, that there's this external time parameter. Let's just say the universe is in a stationary state, it's completely unchanging, so that we can do away with that parameter. And then it turns out they can actually recover everything that we know about dynamics, even from the stationary universe. And there is a completely analogous problem with space, where we assume like there is a thing called space, there's a position that I have in space, and it's a little bit unclear what that should be. Like, what is this? It's like the external, I don't know even what to call it, but there is a like external space. We impose that there is such a thing as my location, my position here. The thing that we never see, we only ever see relative distances, like I am a certain length away from my computer, for example, and it's only the relative distances that seem to matter. For example, when anything interacts with something else, it's only the relative distance between them that could play a role in their interaction. Like with Newtonian gravity, you have this. Anyway, so I think that like we have this explanation of time, which is very neat, works very well. And why is it that we do not have a similar explanation for space? So I think that is a pretty confined question that should have a definite answer. And I hope that there is a model out there, just like the Page-Wooders model for time, which does away with this need for absolute space.
Wonderful. And again, this is in the same vein. What is your favorite area of physics and why?
The favorite area of physics is the area I work on, which is quantum information and kind of related. It's foundations of quantum theory and / quantum information theory. That's my favorite subject.
Excellent. That was from Maria Santos. From David Hearn, if time is emergent, is gravity?
We don't know. We don't have a theory of gravity that is. So in general relativity, time is not really emergent. It's part of space-time. So time is emergent in the sense that it is an aspect of space-time. So time as such does not exist. It's only space-time that really exists in general relativity. But space-time is assumed to be a fundamental aspect of reality. There is just such a thing as space-time within general relativity. So according to GR, according to general relativity, the answer would be no. It's space-time is fundamental. We don't know whether that is the actual definitive answer because we don't have a quantum theory of general relativity. In other theories of time seems to be emergent, like in the thing I just mentioned, the Page-Wooders construction, with where you have a stationary kind of block universe in which time emerges from entanglement. There, it seems to be emergent. It seems to be emergent in other similar constructions, like those to Julian. And what this does is it leaves us with a conflict to which we won't have an answer until we have a quantum theory of gravity. But my guess would be that it is. But it's not.
If you'd like to know more about this, certainly the work of Julian Barber, again, we've mentioned him multiple times. Look up him, look up his books. Sam has written papers on this. I think your PhD thesis might have also touched on this, physics of time. And in fact, you appeared on my podcast, Topcast, and we had a discussion. We went for about more than an hour, I think, about time. So if you want deep dives, there's a lot of stuff out there that Sam has produced and other people have produced about this. But sticking with time, Jitin has asked, how do we know each second is the same period of time? Like, how do we know in an atomic clock that the vibrations are all spaced equally in time?
Yes. So I saw that question. I think it's a very nice question. I think that I believe it was Poincaré had the same question. It was one of his two questions, one of his two problems about time. And the answer I would give is that we have a theory about the behavior of the clock. So there's a thing which we use as a clock, and according to our theory of it, its behavior is I don't know what the right word would be, but homogeneous or something like that, or even. And the point is that even if it weren't from the point of view of something like absolute time, we would never know. So what we see is like certain processes in our bodies, in our minds, in other physical systems behave a certain way relative to the atoms, the atomic clocks, or the oscillations of certain energy levels in cesium atoms or whatever. If it were the case that, for example, the atomic clocks were really oscillating, that they were speeding up and slowing down and things, then we would be doing that as well because of our relationship to them. And so even if that were the case, we would never know. We could never know that were going on. because all we see is the relative change between us and the clock. So it's like if someone were to speed up the entire universe by a factor of 2, so everything is happening twice as fast, you couldn't tell. You would never be able to tell that things are happening twice as fast in a universe where everything is just about the relative changes, because the relative changes would still be unaffected by that, despite the time having really been sped up. We couldn't know. It would feel exactly as we feel right now.
Yeah, I think it's a similar philosophical issue to what if suddenly everything doubled in size? I mean, if everything doubled in size, including all your measuring instruments, then relative to what is everything doubling in size kind of thing? Okay, there's a couple of questions you may not have seen. They've appeared on my feed. There's 2 here from Randy. The first one reads, has Sam looked into the validity or lack thereof for, I don't know if you know this person, Jacob Barandes' indivisible stochastic processes ideas, which Barandes indicates eliminates the need for many worlds theory for double slit experiment results?
Yes, I don't know. I've heard of it, and I haven't looked into it in any detail. So I don't know. I don't have particular criticisms. I would just think, yeah, I would be reluctant to say that there is fundamental stochasticity in the universe. All those theories. I think the way that we understand probabilistic theories is really via many worlds. That is a bold claim I would like to make. Again, this is something really David and also Paul have said as well, that if you think about what does it mean for, what are these probabilities? You have a theory that's probabilistic. Theories that are probabilistic don't say that specific events happen. They just say there is a probability that this event happens, there's a probability that another event happens. They never say event X actually happens or doesn't happen. And I think inherently they are all basically many worlds theories. The probabilistic theories are almost the only way to really make sense of them physically is to say what's going on there is that 2 things are happening at the same time. And otherwise I don't know what they even mean physically.
David does have a wonderful talk. I think it's extremely underrated, underappreciated. It's there on YouTube, Physics and Probability, or something to that effect anyway. It's a series of slides and David's speaking over the slides. And he speaks specifically to this issue about the place of stochastic processes, whether they're real or not in physics, and the role of Everettian quantum theory and sorting out these issues surrounding probability. So I can certainly recommend that to people if they're interested in that kind of thing. Whether or not it answers that particular question, I don't know. But Randy's asked another question. Can Sam explain Penrose's backwards causality conjecture and say what, if anything, he thinks is wrong with that idea?
So I think he's talking about a conjecture Penrose had where he tries to explain how one event, so he's trying to explain things like the Bell inequality is being violated. It's all to do with that locality again. So we have certain correlations between physical systems, and how can it be that they know at a distance what is going on here? And the answer, as we said at the start of the podcast, is the other systems don't know at a distance what's going on here. They only find out when they meet up, and then they see that certain versions of each other are not visible, they can't interact with them. So one answer would be it's not necessary because we have a local account. I think Penrose, to his credit, was trying to, so he said it's something like information about what the state is going to be. I think in fact he was talking about teleportation maybe specifically, but it doesn't really matter. It's all kind of for the purpose of this podcast, the difference are not that important. He was saying something like, well, person here at some distance away from person, so Bob, some distance away from Alice, is affected by a measurement that Alice does, because some information travels back in time through the entangled particle and then travels forward to Bob again. And I think that's the conjecture he's talking about. That's, at least that is a conjecture by Penrose, in which he talks about backwards causation. And to Penrose's credit, he is actually trying to explain something there that is an actual account of what is going on in the universe. But I just don't think we need it. I don't like time travel may or may not be possible, but in this case, it's not necessary to invoke anything like that, because the solution is just much simpler.
Mm-hmm. A question from Convex Bets, also on a theory from someone else. Would love to find out if Sam is familiar with Eric Weinstein's theory of geometric unity, and get his opinion on it if he does.
I've tried to listen to a talk about that at some point, and I don't know. I don't understand it. I don't know anything about it, I'm afraid.
I think that, if you go onto YouTube, someone, Eric Weinstein, recently retweeted a fellow whose business on social media is to go through various theories of everything, and his latest discussion of a theory of everything just so happens to be this geometric unity thing. I can't attest to how credible this guy is, but at least I think he might be at least mathematically adept enough to understand what Eric's getting at there. Someone has asked in the chat, Gaurav has asked, is there any relationship between fungible instances of me splitting into branches and the choices I make?
Yes, there is, but it might not be what you think. The reason is, if you make choices that are based on a good explanation, you should expect there to be less branching. So the better your explanations are for what to do, the less you'll be affected by random chance. Like for example, my favorite way of thinking about this is to show that knowledge makes branches converge. Is, let's say that I get into a car accident. In one universe I avoid a car accident. In another universe I am in a car accident and I break my arm. I go to the doctor. They set my arm. They give me medication. I don't get an infection. A couple of months later, I'm back to being healthy. And it's a bit lost time, but otherwise I'm almost the same as I was in the universe in which I completely avoided being in the car accident. Then you can see that these universes are very much alike to one another. So although there is branching going on, so there are different versions of you, and these different versions of you branch regardless of your choices, I should say. They will be very similar if you have knowledge. The more knowledge you have, the more similar you should expect all of these branches to be. So I should clarify, the branching itself will just go on regardless of whether or not you're making choices. But the way that, how similar you are in different branches is determined by your knowledge.
An associated issue there was that of the people who didn't attribute Trump's near assassination to the hand of God moving down and causing the bullet to just graze his ear, the people who wanted to talk about the multiverse and to say that we were in a very tiny sliver there where Trump happened to survive, and most of the times he was dead. And David Deutsch pointed out, well, hold on, in most of the rest of the multiverse, the assailant would have been caught prior to getting on the roof and getting the gun and getting anywhere near shooting thing. And so therefore, Trump survived across the multiverse in any case, and probably only in a tiny sliver did he actually end up dying, and were things completely different. So I think that accords in the same way, that these rare instances are nonetheless rare anyway. And then people have, when it comes to choice, have consistent personalities. So although you might make a very infrequent decision at some point during your life, for the rest of your life you're sort of doing a very similar thing. And so, yeah, but this whole question of personal identity in the multiverse is nonetheless fascinating, I think.
Yeah, I agree. It's something that you would think philosophers would be writing about all the time.
Okay, I think we have exhausted questions from the audience, unless anyone wants to ask any final ones. But is there anything else you'd like to tell us about what you're working on? At the moment, you're at the University of Montreal, I think. And how much longer are you there for, and what are you doing while you're there?
So I'm here for a little bit less than a year still, and so a couple of months left. And I am working on, trying to formalize, as I said, there's this idea of locally inaccessible information. That's a very nice idea that David Deutsch and Patrick Hayden had in a paper of theirs in 2001, even earlier, I think. The paper probably appeared in 1999 on the archive. And it's a beautiful idea that there's information that can be inside a system without it being retrievable from that system on its own. You need like locked in there, and you need a key to unlock it with. And I hope to make that a bit more precise using certain mathematical tools developed by Paul Raymond Robichaud.
That's excellent. I'll have something else I'll be able to tweet out every time someone decides to invoke spooky action at a distance, or talk about entanglement and weird other effects that consciousness has on the collapse of the wave function or whatever. Okay, well, thanks very much, Sam. This has been absolutely fantastic in terms of explaining not only your work, but the role of the Conjecture Institute in supporting researchers such as you. And hopefully we'll be able to do this again. And in the meantime, I just say to the audience that stay tuned here on the Conjecture Institute live stream over the coming weeks and months, where eventually I'll get through all of the fellows and we'll find out what they're doing and how Logan and his team are supporting people across a diverse range of areas and allowing them the freedom to just explore ideas, all of whom have in common this commitment to a critical, rationalist, creative view of how knowledge is actually generated. Thanks very much again, Sam, and talk to you again soon.
Sounds good. Thanks so much for having me.
Bye-bye.